It's better now? I think there was some issue with the mic, but I hope it's fixed now. Alright, so without wasting any further time, let's start. So this was the last question that we did in the previous class, right? Find the number of ways of selecting 3 people out of 10 people sitting on a round table such that no 2 people selected are consecutive. Alright. So, how did we solve this? We assigned, there were 1, 2, 3, 4, like this, 10 people sitting around a table, and we assigned them ones or zeros. If we assigned this person 0, that meant that we are not going to select this person, or we are going to select this person, and if we gave this person a 1, that meant that we are not selecting this person stays here, right? This was how we did it. We divided it into 2 cases. One case that we select this person, one case we do not select this person, and based on that we got our final answer. Correct? Now let's take a look at this from another way, a familiar way. Whenever we had to let's say solve a problem where no 2 A's are adjacent, we can either fill these 2 A's between the gaps, or we can check how many cases do we have when these 2 A's are adjacent and remove those cases from the entire total cases, right? So basically what we do not want here, what do we not want? We do not want to select consecutive people. So we are going to check how many ways are there to select consecutive people, and then that's it. We can just remove those cases from the entire set. What are the total number of ways of selecting 3 people out of 10 people sitting around a round table? Without any condition, we know the answer is 10C3, right? 10C3 ways of selecting 3 people out of 10 given people. Now, how do we find the cases that we do not want to include? We want to exclude. So that is where inclusion, exclusion is coming from. What do you want to include? What do you want to exclude? So here I want to exclude the cases where any 2 adjacent people are selected. Okay. So again, number of ways of counting that. I will do it in this way, that I first check number of ways of selecting 3 adjacent people, and case 2 will be 2 adjacent, 1 non-adjacent, right? If we cover both of these cases, then we are counting all the possible cases where 2 adjacent people are selected. So now, how many ways are there of selecting 3 adjacent people? Let's say I start from this person and go in a clockwise direction. This is my first person, second and third. This is one case. If I start from, let's say here, and go in the clockwise direction, then 1 person, 2 and 3. So as soon as we fix the first person, and another way of looking at this is, let's say I'm choosing this, this and this. These 3 persons that are marked with blue, these are the 3 adjacent. I want to see, how do I make sure that I include this? I only count the first person and then go clockwise. So as soon as I fix the first person and go in the clockwise direction, I know which 3 adjacent people to choose, right? So that means all I need to count is how many ways can I fix this first person. In how many ways can I fix this first person? 10, because out of all these 10 people, I can fix any one of them, and as soon as I fix them, I get 3 adjacent people. So that means case 1 has 10 possibilities. There are 10 ways of selecting 3 adjacent people, because as soon as you fix one person, you get a unique possibility, a unique arrangement, because you're only going in one direction. If you were counting both the directions, then you would see repetitions. Okay, so that's something we have discussed in previous classes. In case of a circular arrangement, fix the direction to avoid repetitions. So I fix the direction, clockwise, anti-clockwise, whatever you want it to be, and then I have unique arrangements. Coming to the second case. In the second case, I want 2 adjacent and 1 non-adjacent. Just like before, I can have 2 adjacent in the same ways, right? I'll draw the circle again. So now, as soon as I fix the first person, I know which 2 adjacent I'm talking about, right? I go in the clockwise direction and I know which 2 adjacent people I'm talking about. If I fix this person, then I'm talking about these 2. If I fix this person, then I'm talking about these 2. So as soon as I fix one person, I know which 2 adjacent people I'm talking about. Now comes the third person. So that means I can select this in 10 ways, right? Now for each of such pairs, we need 1 non-adjacent, right? So that means this person cannot be included, this person cannot be included, because that will be adjacent to this, that will be adjacent to this, and that is something we have already counted. It's not like that is allowed. That is also not allowed, but we have already counted 3 adjacent. Now we are talking about 2 adjacent and 1 non-adjacent. So that means this person cannot be counted, this person cannot be counted out of the remaining 6, right? 1, 2, 3, 4. These 4 are just removed from the selection pool. Out of the remaining 6, we can select anyone, right? We can select any one of them and we will get a unique case of 2 adjacent and 1 non-adjacent. Okay, so that means for each pair we get 6 C1 options. So in total 60. Now our original total number of cases. The total number of cases that we had was 10C3. 10C3 is equal to 10 into 9 into 8 divided by 3 into 2 into 1. So this comes out to be 120. Out of these 120, we have to remove 10 plus 60, that is 70. So the final answer is 120 minus 70 equals 50. Same answer, of course, the same answer. That's the whole point, right? If your method is correct, you are going to reach the same answer. There is only one correct answer, but there can be multiple correct methods. So, of course, you can choose any of those methods and they are fine. But all I want you to understand is if your mind started thinking of this, because I know right now we're studying topic by topic, you're looking at questions one by one, you're looking at a topic, some theory, and then you're looking at a question. Then you know how to apply, which method to apply, how to solve that question, right? But what if you see this question out of nowhere? You don't know in that case which method to apply. You can think of multiple methods. You don't know which one to apply, but the first method you think of, you want to see, can I get the correct answer through this method? So for example, if you saw this question and you're thinking, I want to select 3 people such that no 2 people selected are consecutive. Let me just count. It makes sense that I can just count how many consecutive people I can select. I can use the bundle method, right? And then I can probably just exclude those cases and I'll have my answer. So I wanted to tell you how you can actually use this method. This is This will take just as much time. I took more time to explain this because this is the first question today, and this might be new theory for a lot of you students here, but this is very important, very simple. Sometimes it can happen that only one method gives you the right answer, the other method, not because the method was wrong, but because you missed something, it became harder to make sure that you're counting only the unique cases. So that is why it's very important to understand all the methods, how to count the number of adjacent, 3 adjacent people, the number of 2 adjacent, 1 non-adjacent. All of these will be very useful. So I hope this was very clear. I took my sweet time explaining this problem so that you can apply this knowledge anywhere, in any problem. Okay, now coming to the generic inclusion, exclusion. What is inclusion? What is exclusion? If you have studied sets, if you have studied Venn diagrams, then this is very easy. But if you haven't, I'll give you a little bit of intro. So, inclusion, exclusion for 2 sets. We have A and B. These are 2 sets. This is a Venn diagram for the 2 sets where this blue circle represents the set A, B circle represents the set B. This overlap is what is common between A and B, which we represent by A intersection B. Okay, now we want to count the number of elements, the number of members in these 2 sets combined. We count these and these, we write all of them together, and we want to count what is the total, that either it's in A or in B or in both, but at least one of them. So we want to count the number of elements in these 2 sets combined. So we write that as union. That means A or B, both is also allowed, but at least in one of them. It should be there in at least one of them. So we want to count the number of elements in A union B, which is either A or B or both. That is counted as, we first take all the elements that are in A and all the elements that are in B, but we counted the elements that are there in both of them twice, right? We first counted the entire elements in blue circle, then we counted all the elements in orange circle, but this common area, we counted this twice. We only needed to count them once, so we will subtract this once. So n of A plus n of B minus n of A intersection B. That is how we calculate the total number of elements in either A or B or both, at least in one of them. This outside, the rectangle outside this is called universal set. Universal set is all the elements that could have been there, that we are talking about, all the elements that could have been there. For example, if A is, let's say, all the maths teachers in your school, B is all the chemistry teachers in your school, and let's say there are some teachers who are teaching both maths and chemistry. Universal could have been all the teachers in your school, or all the science teachers in your school, all the science and maths teachers in your school. It can be anything, but all the elements of A and B are there in universal set. So what is this area outside both these circles, which is neither in A nor in B? It is A union B complement. A union B complement, that means neither in A nor in B. Complement is not in this. So not in A union B, that means it's not in any of these circles. So if we want to count the number of elements in this, that is neither A nor B. This is neither A nor B. Then we will just simply do n of u, all the teachers, all the elements that were there in the universal set, all the total teachers that we were talking about, all the total elements we were talking about, and subtract the ones that were there in A union B. Okay, so we'll see how we can apply this formula directly here. Find the number of positive integers from 1 to 100 which are divisible by at least one of 3 or 5. That means in our Venn diagram, U is 1 to 100. All positive integers from 1 to 100. We are talking about all these natural numbers. A is multiples of 3. B is multiples of 5. What is this common area? This A intersection B, what does this represent? What does this represent? Yes, bacha, I see the answer, but that is not the answer what I'm asking. Very good if you've already solved it, but it's very important to answer what the teacher is asking and not just look at the question and solve it. Very good if you were able to solve this. But what is A intersection B? What did you calculate when you were trying to solve this problem? What is A intersection B? That is there in both these sets. It is a multiple of 5 and multiple of 3. It's multiple of 3 and a multiple of 5. So that means it is multiples of 50, right? So it is a multiple of 3 and it is a multiple of 5. That means it has to be a multiple of 50. Good. So now what do we need to calculate? We need to calculate the number of positive integers. We don't want to see which integers are there. We need to count the number of integers, the number of elements in either A or B or both, at least one of them. That means we need to calculate this. That is equal to n of A plus n of B minus n of A intersection B. Correct? Now, what is n of A? N of A is how many multiples of 3 are there from 1 to 100. Right? From 1 to 100, how many multiples of 3 are there? That is nothing but greatest integer of 100 by 3. We used this in the last class. Very similar concept, right? When we were counting the exponent, we were calculating the exponent of a prime number. In the same way, how many 3's are there? How many multiples of 3 are there? 100 divided by 3, greatest integer of that, which is 33. What is n of B? By the same logic, 100 by 5. There will be these many multiples of 5 in 1 to 100. So, plus 20 minus n of A intersection B. A intersection B is multiples of 15. So, how many multiples of 15 are here? 100 by 15, greatest integer. So, that is 100 by 15, greatest integer, 6. So, finally, we get our answer. So, yes, bache, you were getting the right answer. Very good. So, this is how we can use this simple formula to calculate all the multiples of 3 or 5. We don't actually have to see how many are there. But if you were going logically, if you did not know this formula, even then you could have calculated, right? You counting, okay, all the multiples of 3. There's 3, 6, 9 up to 99. So, that is 33. Okay. And there, how many multiples of 5 are there? There's 5, 10, 15, 20, up to 100. Okay, so 20. But I counted 15 twice, then 30 again twice. So, which means I'm counting multiples of 15 2 times. I only needed to calculate 1 time, right? So, I will remove all the multiples of 15 because they were counted twice. So, I can subtract the number of multiples of 15, which is 15, 20, 30, 45 up to 90. So, that is 6. So, I would get 33 plus 20 minus 6. Very logical, right? Okay. So, now this was when we only had 2 sets, multiples of 3 and multiples of 5. What if we have more than one set? What if, let's say, we have 3 sets? The Venn diagram is very similar. Now you have, the rectangle is still a universal set. We have three, let's say, physics teachers, maths teachers, chemistry teachers, right? So we have these three circles. Now there could be that there are some teachers who teach physics as well as maths. So let's say if this was P, this was M, and this was C, chemistry, then this entire overlap between P and M are the teachers who are teaching both physics and maths. P and C, these are all the teachers that are teaching both physics and chemistry. And similarly, maths and chemistry, these are the teachers that are teaching both maths and chemistry. Now if you look in the center, this triangular area, we can see yellow, orange, green, all three colors. That means they are teaching physics, they are teaching maths, and they are teaching chemistry. It's there in all the three circles. That means this is A intersection B intersection C. They are there in all of them, A and B and C, like that. Okay, so this is how you understand the Venn diagram. Now coming back to our problem, we need to calculate an A union B union C. That in at least one of them, it should be there in at least one of them. How many such elements do we have that are there in at least one of them? Now, just like before, we count all the elements of A, all the elements of B, all the elements of C. Okay, now just like before, I counted this A intersection B twice, so I'll remove that. I counted B intersection C twice, I'll also include that. And I counted A intersection C twice, I will also include that. But this central area, A intersection B intersection C, first I counted it 3 times, right? Once in A, once in B, once in C. I counted it 3 times. Now, when I was removing A intersection B, I removed 1. When I was removing B intersection C, I removed another one. And when I was removing C intersection A, I removed another one. Now it's completely gone. So we need to at least include it once. So we will add an A intersection B intersection C. And like that, we get the formula for 3 sets. So bache, this kind of a formula where we first take 1 at a time and add them, then subtract 2 at a time, then add 3 at a time. So this is the generic formula that you're going to get for any number of sets. Okay, so for example, if you have, let's say, 4 sets, so we need to calculate an A union B union C union D. What are we going to do? We're going to first add all the number of elements taken 1 at a time, in sets taken 1 at a time. Okay, now we have to subtract 2 at a time. So minus A intersection B. Now how many such will be there? We have to select 2 out of 4. 4C2, 6. So these are all the 2 pairs that we could have got from these 4. So we subtracted. Now we have to add 3 taken at a time. So plus 3 taken at a time, 4C3, there will be 4 such triplets. So A intersection B intersection C, B intersection C intersection D, C intersection D intersection A, and A intersection C intersection D. Basically, we're leaving out 1. If we're taking 3, we're skipping 1. So we either skip A, or we skip B, or we skip We either skip A or B or C or D. So we have 4. Now we added this. Now this was 3 at a time. Now we come to 4 at a time, and what was the order? Plus, minus, plus, next will be minus. 4 at a time, that means we're taking all 4. And like this we get the formula for any number of sets. Okay, so the same formula, the same pattern will be followed for any number of sets. That is what inclusion exclusion is. We included, then excluded, then included, then excluded. Okay, so we cannot go further after this because we've taken all 4. We cannot go to 5 at a time because there are only 4 sets. So if you want to verify, we were taking 1 at a time, then subtracted 2 at a time, and that's it, we only had 2. For 3, we took 1 at a time, subtracted 2 at a time, added 3 at a time, and that's it, we stopped here. So like this we can do inclusion exclusion for any number of sets. Okay. Now find the number of positive integers from 1 to 100 which are neither divisible by 3 nor by 5. That means if A was multiples of 3, B was multiples of 5, and we want neither divisible by 3 nor by 5. That means this outside region. What was this? A union B complement, and if we needed to calculate the number of elements in this, all we had to do was n of U minus n of A union B. What is n of U? All the numbers. 100. Right? That's what we're talking about. Positive integers from 1 to 100. So our universal set is all natural numbers from 1 to 100. Then neither divisible by 3 nor by 5. So that becomes n of U minus n of A union B. That is 100 minus, what did we calculate? If let's say we were going from scratch, we did not just calculate this, then n of A plus n of B minus n of A intersection B. So like this we get 100 minus 47, which is 53. Alright, so like this we can calculate either in 3 or in 5 or in 3 but not in 5, like that. For example, if we want to calculate from 1 to 100 only divisible by 3 not by 5, in that case what does our Venn diagram look like? This is U, this is still 1 to 100, this is A multiples of 3, B multiples of 5. Now what area are we talking about? We are talking about divisible by 3. That means it's in set A but not by 5. So not in B. In set A but not in set B. In that case we just want this area, right? Because it has to be in A, so it has to be in this circle but not in the B circle. So that means we will remove the common parts. So what will be the answer? The answer will be n of A minus, what did we subtract? We did not subtract the entire set B. We only subtracted the ones that we had included but we did not want to include, which is A intersection B. So that comes out to be n of A was 33, n of A intersection B, that is multiples of 15, was 6. So we get our answer 27. Alright, so that way using Venn diagrams you can very easily, very simply solve any such problems. As soon as you have your set, you know which sets to assume and what is the common area, then you just have to follow the inclusion exclusion principle. Alright, now let's say we want number of positive integers from 1 to 100 which are neither divisible by 2 nor by 3 nor by 5. That means we have 3 sets: A that are divisible by 2, B that are divisible by 3 and C that are divisible by 5. Right? Something like this. U is again 1 to 100. Now what are we doing? We are just using our formula. So to use the formula, that is n, what do we need to find? N of U minus n of A union B union C. Right? That is what we need to calculate, that are neither divisible by 2 nor by 3 nor by 5. That means we will exclude all of those cases that are divisible by either 2 or 3 or 5, at least one of them. Right? We'll remove all of them. So that is what we have to calculate. Number of elements in U, 100. Number of elements in A union B union C. We first take one at a time. Right? One at a time. N of A is 100 by 2, 50. Then N of B is 100 by 33, greatest integer 33. N of C 20. We'll subtract taken 2 at a time. Now what is 2 at a time? Just like before, A intersection B, divisible by 2 and divisible by 3, that means divisible by 6. Like that, B intersection C 15, C intersection A divisible by 10. So we will subtract those. So divisible by 6, 100 by 6, we'll do that. So that gives us 16. Divisible by 15, 6, and divisible by 10, 10. Then taken 3 at a time, now we have to add. So taken 3 at a time, that is divisible by 2 and 3 and 5. So that means they're divisible by the product of 2 and 3 and 5, that is 30. So how many such numbers? 100 by 30, 3, 30, 60 and 90. So we will add those 3. And that is how you can calculate this. So 50 plus 33, 83 plus 20, 103 minus 16, that is 87, minus 6, 81, minus 10, 71, plus 3, 74. So we are subtracting 100 minus 74, that is 26. Is that what everyone's getting? Yeah. Very good. So this is how you can use the formula and not have to write all of it. Just do it mentally. But if you think that can make you just do some mistakes, cause some mistakes, then just simply write everything and make sure you don't make a mistake. Okay? But an important thing here is to understand the meaning of sentences and how to transform that into the language of sets. Union, intersection, complement, that is the most important thing. Once you know, then you know the formula. That becomes very easy. Alright. Now a very important application of derangement, of inclusion-exclusion principle is derangements. What is derangement? Derangement is such that, let's say, we have n objects. Let's say we have n students and each of them, we have 6 students and each of them is assigned one seat. Okay, each of them is assigned one seat. Now I want to see how many ways of arranging these 6 students are there such that none of them is sitting in their original seat. Okay, for example, let's say maybe they can hide something in their own seat for an exam, and I don't want that. I don't want that any of the students can cheat using something they had written on the desk for their help. So I want to make sure that none of them can do something like that, so none of them will be sitting in their original seat. Now how many ways of arranging these 6 students like that are there? So that is called derangement, where none of the students are sitting in their original seat. If we had letters and envelopes, each letter was supposed to go in its corresponding envelope, but I want to see how many ways are there when none of the letters go in their respective envelope. So like that is what derangement is. Very important, you will see it from time to time in a lot of questions. So how do we calculate that? That is nothing but inclusion exclusion. How many ways of arranging n distinct objects in n places are there? Without any condition, there are n factorial ways of arranging n objects in n places. Now we are obviously choosing those ways as well where some of the students are sitting in their original spots, maybe all of them, maybe some of them, maybe one of them, two of them. Let's see. So let's say I want to now remove those cases, right? So how do I remove those? I will check. I want to remove those cases where one of them is sitting in their original spot. So I will choose which one is sitting in their original spot, and then now I know this one person is sitting in their original seat, in its original place. The remaining n minus 1 can be anywhere. But this also includes when two of them are sitting together, two of them are sitting in their original place. We are counting those, right? We are basically repeating certain cases that we are counting. So now we excluded those. Which ones did we exclude? We excluded where these two students were sitting in their original spot. So we will add that NC2 because we excluded it more than once. We had two excluded, but we did not exclude it exactly once. So we will have to add that. Right? And just like that, you will keep going until you reach that situation where all of them were sitting in their original spot. And that is how you get the formula. Okay, this is what inclusion exclusion is. Now, if you look at it, what will be the sign of this? It's alternating between plus minus, so depending on if n is even or odd, it could be plus or minus, right? So we write that as, if it's odd it's minus, if it's even then it's plus. So we will write this as plus minus 1 raised to power n into NCN 0 factorial. Now this might be a bit complicated. How do we actually check? How do we actually calculate? Because these are a lot of calculations, right? So we will simplify each of these terms. N into n minus 1 factorial, that is n factorial, plus n factorial divided by n minus 2 factorial into 2 factorial into n minus 2 factorial. So n minus 2 factorial gets cancelled and we are left with n factorial divided by 2 factorial. Similarly here, n factorial by n minus 3 factorial, 3 factorial into n minus 3 factorial, even this gets cancelled. So like that we will have n factorial by 1 factorial, 2 factorial, 3 factorial, 4 factorial up to n factorial, right? We will be doing, we'll just cover the entire syllabus in a few classes and then we will go through all the PYQs, all the relevant questions for this chapter after that, but first we need to cover, because if we are doing the question simultaneously, then you know which method to apply, how to solve that question. But if you see a new question randomly, then how will you solve it? So that is why we will solve all the questions at the very end. Do not worry, we will have a lot of such sessions just for problem solving. But for now, let's understand where we're getting the formula. Okay, so like that, we have n factorial minus n factorial by 1 factorial, n factorial by 2 factorial, and so on. And this is actually minus 1 raised to power n factorial by n factorial. So if we take n factorial common out of all of these, then we have this formula n factorial into 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial up to minus 1 raised to power n 1 by n factorial. So like that we have our formula. So that means we write this as dn. So that means d1 will be calculated like 1 factorial 1 minus 1 by 1 factorial, and that's it. We stop here. We won't go to 2 because n is 1. So that means our answer is 0. Does that make sense? Of course it makes sense, right? Because we had one student and one place. We want to see how many ways of arranging this one student in this one place is there, such that it's not sitting in its original position. There is no such possibility. So D1 is correctly 0. Now D2. D2 is, there's S1 in place P1, there's S2 in place P2. We want such an arrangement such that these two are not sitting in their original spots, which means S1 has to sit here and S2 has to sit here, right? Only one possibility. Let's verify, is that what we are getting? 2 factorial by 1 minus 1 by 1 factorial plus 1 by 2 factorial. So yes, this comes out to be 1. Correct? Similarly, let's see D3. D3, in that case we have P1, P2, P3. Now S1 cannot sit here. S1 can sit here or here, right? Only two possibilities for S1. For S2, let's see in the first possibility. Now S2 can go anywhere, but if S2 goes here, let's say S2 goes here, then S3 will have to go here. That means it will be in its original spot. That is not allowed. So that means S2 has to go here so that S3 can go here. Similarly here, S2 cannot go here, S2 has to go here, which means S3 will go here. So only two possibilities are there for 3 objects. Let's verify. 3 factorial by 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial. So this is 0. We'll multiply this entirely. So this becomes 0. So that means 3 factorial by 2 factorial, 3 minus 1, that is 2. Correct? So like this, you can verify this for any number. But an interesting way of looking at this is, let's say we want to derange n objects, right? Now, we want to derange n objects. How many ways are there? If I know n minus 1, I know dn minus 1. Okay, so that means I know if I have P1, P2 up to Pn, And similarly, I have Sn objects. I have n objects. I have S1, S2 up to Sn. Now, S1 can go. Where can S1 go? S1 cannot go here, but S1 can go anywhere from P2 to Pn, right? So that means I have S1 I have n minus 1 options. Once I have placed S1 in one of these positions, then let's say I chose Pk out of 2 to n. So k can be anything from 2 to n. Let's say I picked Pk. How many options were there? N minus 1. I chose kth position for S1. Now, where will Sk go? Sk anyway could not go anywhere in. Now, where will Sk go? Sk can either go to P1, right? Or not at P1. Only these two possibilities, either it goes to P1 or it doesn't go to P1, both are allowed. Now, if Sk goes to P1, that means I removed two of the elements, two of the objects, and the remaining problem remains the same. Now I have n minus 2 objects that cannot sit in their original positions, and their original positions are available, right? So that means I have dn minus 2 ways of arranging the remaining objects, right? Now in this case, when Sk does not go sit at P1, that means I have n minus 1 positions and n minus 1 objects, and Sk cannot go to P1 and the remaining cannot go to their original. Let's say if P1 was its original position, then it's very similar to our n minus 1 derangement, that Sk cannot go to a specific position, the remaining cannot go to their specific positions. It is the same as n minus 1 objects cannot go, being able to go to their respective positions. So that means this is dn minus 2 ways, this is dn minus 1 ways, right? So that means for S1, I had n minus 1 options, and once I had n minus 1 options, once I selected that, then it was dn minus 1 plus dn minus 2, right? So this is how we can understand derangement, that it is not just placing. Sk cannot go to Pk, Sk cannot go to a specific position. So let's look at an application, an example, and it will be more clear, and then we're going to come back to this. So first of all, find the number of placing 5 letters in 5 envelopes such that no letter goes in the correct envelope, right? No correct envelope, that means it's D5. So you simply calculate 5 factorial by 1 minus 1 by 1 factorial plus 1 by 2 factorial minus 1 by 3 factorial, like this. So that becomes, this is always 0, 1 minus 1. So 5 factorial by 2 factorial, that is 120, 1 by 2 minus 1 by 6 plus 1 by 24 minus 1 by 120. So we multiply 60 minus 20 plus 5 minus 1, that is 44. Okay, so because these are very simple, and you might use them again and again. So you can memorize these. You might actually end up remembering these because you will be using these simple numbers derangements, but again, up to you. If you don't memorize it, that's also fine. You can just simply calculate using the formula that we had. So D1 was 0, D2 was 1, D3 was 2, D4 is 9, D5 is 44, D6 is 265. Like that, you can maybe remember some of these. Now, let's say we have a similar problem now, 6 cards, 6 envelopes. Each envelope contains exactly 1 card and no card is placed in the envelope bearing the same number. Derangement. Now there's a condition. The card numbered 1 is always placed in envelope number 2. Card 1 goes to envelope 2. Total number of ways of doing this. We did this very similar thing just now. Now K is 2. So now C2 can either go to E1 or it cannot go to E1. For C2 going to E1, now this is D4, Dn minus 2. If it cannot go to E1, then it is n minus 1. So D4 plus D5, that is 9 plus 44, that is 53. Right? Another way of looking at this is when we had these 6 envelopes. Card 1. Where could card 1 go? Card 1 could have gone here, or here, or here, or here, or here. 5 options. There is no difference between them, right? There are exactly 5 options for card 1 and it could have taken any one of them. So for each of them, it's an identical situation. For any K, we get D4 plus D5, right? It doesn't matter where it goes. These are just numbers. It can be in any order. It could have gone in any one of those. That meant there are total 265 ways, right? D6 is 265. That is equal to 5 times C1 going to EK. It doesn't matter what K we chose. If it is K2, then we will get the same number of possibilities. If K is 3, we get the same number of possibilities. So there were 5 options. For each of them, same number of possibilities. This is what we are trying to calculate for E2. So we just divide 265 by 5. So 265 by 5 is equal to 53. Right? Both are correct. Both are important to understand. If you understand this, then we can go back to our formula. So that means D6 can go for, we take any one of them. We take any card. First card, we took first card and we see that C1 could have gone to any of these 5 envelopes. And for each of them, it would be identical. There's not much difference, right? Once it's gone there, then there will be same number of possibilities. So that number of possibilities is into 5 is 265. So 265 divided by 553, that is the number of possibilities of derangement once we know that C1 is going to E2. So coming back to our this thing, that means once we took any one of them, we took S1, any one of them, and we saw there were n minus 1 options for that one object. It just cannot go to P1, and then it has n minus 1 options, and for each of those options there are dn minus 2 plus dn minus 1 options. So this is nothing but equal to dn. The total number of derangements is, we are trying to find a recursive formula for this. So once we have one object, we take any one, and we find either S1 can go to P2, or it can go to P3, or it can go to like that Pn. And for each of them there are Dn minus 2 plus Dn minus 1 options of arrangements, possibilities, and we multiply that with n minus 1 and we get all possible derangements. So if you want to verify, you can verify. Dn by n minus 1 is equal to Dn minus 1 plus Dn minus 2. If you want, you can verify, you will get the same value on either side. Okay, so that is how we can even get the recursive thing. So for example, now we know if we just need to calculate D7, we just do 6 times D5 plus D6, right? So D5 plus D6, that is 44 plus 265, 309. So 6 into 309. If you want to verify, you can verify. D1 is 0, D2 is 1, D3 will be 2 times D1 plus D2. 0 plus 1 into 2. This is 3 times D2 plus D3. D2 plus D3, 3 into 3, 9. 4 times D3 plus D4. D3 plus D4, 11 into 4, 44. 5 times D4 plus D5, that is 53 into 5, 265. So like this you can calculate any derangement either using the formula, or if you know these values, then it becomes even easier. Correct? So with this we are going to end our class today. We are going to we have basically covered all the basic topics, including multinomial, but I think some students might still be confused in multinomial because we did not properly discuss those, we did not cover more questions. So I will discuss multinomial in the next class, as well as some topics which are not in JEE. So yes, all you Olympiad, this is a Olympiad students here, this is an Olympiad level course. So if you were referring to this for JEE, then more or less you're done with the theory. But if you are, as it's intended, studying for the Olympiad, then we will do the other topics, the advanced topics that you have to just learn. Again, very easy, very understandable, very logical. We will just discuss all of those things and solve more questions than today, right? Today was more theoretical, but it was just as important. In the next class, we will try to cover the entire theory, and then from the class after that, we will be solving a lot of questions. So come prepared, make sure you revise all of this so that you are not struggling to understand the topics that we will do in the next class, and definitely the questions that we will be discussing, because they will not be this straightforward, they will not be this easy, they will be a bit tricky. Alright, so let's end the class here. I hope this was very informative. Even if you knew the basic inclusion exclusion principle, even if you knew the basic derangements formula, I hope you learned. I hope now it's very clear to each and every one of you how actually they are derived, how we can actually see, even if we cannot use the formula directly, we can use the derivation. For example, in this question, we could have, if we knew how it was derived, we were able to solve using any of these methods. They both derivation in a way, right? How we were checking dn is equal to n minus 1 into dn minus 1 plus dn minus 2. This is directly used in this problem. So make sure you revise everything we covered today, and I will see you in the next class. Bye.